Have you ever used an AI and just thought, how is this even possible? It kind of feels like magic, right? Well, you've come to the right place. Today, we're going to crack open that black box and peek inside. And what we'll find isn't magic, but something, honestly, even more interesting. Let's dive in.
We see AI writing poetry, coding, creating incredible art. It really feels like it understands us. But does it? Really? What is actually happening inside that machine when you type in a question and get a perfect answer just seconds later? That's the big question we're going to tackle today.
All right, here's our game plan. We'll start with what I'm calling the illusion of intelligence. Then, we're going to peek inside the artificial brain. From there, we'll see how it turns our language into numbers. Then we'll get to the big one, the self-attention revolution. That's a game changer. And finally, we'll put it all together and see how it all works.
Okay, let's kick things off with this idea, the illusion of intelligence. And here's something that might surprise you. Language models are not new, not at all. Think about the autocomplete on your phone. That's a language model, just a really simple one. But as we all know, something major changed recently, something that made these things feel, well, so much more real.
So what was that big change? Well, it really boils down to two key things, scale and capability. Today's large language models are just unimaginably bigger than the old ones. It's like going from a small-town library to having the entire internet ingested into its memory. And that incredible scale didn't just make them a little bit better, it fundamentally changed them, unlocking brand new abilities that nobody saw coming. And this leads to this really fascinating phenomenon called emergent properties. You can think of these as surprise skills. Seriously, nobody explicitly programmed these AIs to, say, write a funny joke or explain quantum physics. These skills just appeared. They emerged from the sheer scale of the training. Here's a fantastic way to wrap your head around it. Picture a master chef. This chef hasn't just memorized 1,000 recipes, no, they've developed a deep, intuitive understanding of how ingredients work together. So when you throw a bunch of random ingredients at them, a prompt, if you will, they can whip up something totally new and delicious, something they've never made before. That's what an LLM is doing with words. So how in the world do these emergent properties actually happen? Where do they come from? To get that, we have to go a layer deeper. We need to look inside the artificial brain itself. And at the very heart of an LLM is a structure called a neural network. And a neural network is, well, it's pretty much what it sounds like. It's a huge, interconnected web of artificial neurons. And the entire concept is directly inspired by our own brains, right? Where billions of our neurons are constantly firing, connecting, and communicating with each other. The parallel here is actually pretty striking. In our brains, a neuron receives a signal, processes it, and sends out another signal. An artificial neuron, it does the exact same thing, but instead of electrical signals, it's using data and mathematical functions. It's a really elegant digital mimic of a biological process.
So you can imagine each of these little artificial neurons, or nodes, as a single worker on a massive assembly line. Each worker has one very, very specific task. It takes in a piece of information, does a quick little calculation on it, and then passes the result on down the line to the next worker. Okay, but how does each worker know what to do? How important is the information it's getting? That's controlled by something called weights. And the best way to think about weights is like a million tiny volume knobs on a giant mixing board. During training, the network is constantly tweaking these knobs, turning some signals way up, others way down, trying to find that perfect mix that leads to the right answer. This is the learning process, right here. Now, all these workers and knobs aren't just a big jumble. They're organized into layers. And honestly, the easiest way to picture this is as a sandwich. Seriously, your prompt, what you type in, that's the bottom slice of bread. That's the input. Then all the magic, all the calculations, that's the filling. Those are the hidden layers. And finally, the answer it gives you, that's the top slice of bread, the output.
Okay, so we've built this artificial brain made of nodes and weights. But there's a big problem. This brain only speaks one language, and it's math. It only understands numbers. So, how do we get it to understand human language, words, sentences, ideas? This is the next crucial piece of the puzzle. While the very first thing the model has to do is chop our language up into smaller, manageable pieces. These pieces are called tokens. You can think of them as the fundamental building blocks, like the atoms of language from the AI's perspective. They're the smallest units it can actually process.
And here's a really important point. A word is not necessarily a token. They aren't one-to-one. For example, a simple word like cat might be one token, but a more complex word like unbelievable might be broken into 3 tokens,
believe, and able. This is how the AI actually sees our sentences, not as words, but as a sequence of these tokens.
All right, so we've got our stream of tokens, but they're still just pieces. How does the AI attach meaning to them? This is where a truly brilliant process called embedding comes into play. What it does, essentially, is it gives every single token a numerical address, a set of coordinates, and places it on a massive, high-dimensional map of meaning.
And just imagine this map is like a grand, infinite library. Words with similar meanings, like king and queen, or puppy and kitten, are placed right next to each other on the same shelf. Words with related concepts, like king and throne, are nearby. But words with opposite meanings, like hot and cold, they're on completely opposite sides of the library. This giant spatial map is how the model learns the rich, complex relationships between all these different concepts.
Okay, great. The AI can understand the relationships between individual tokens. But language isn't just a list of words, right? It's about sentences, context, nuance, grammar. And for a long, long time, this was the biggest roadblock in AI. Solving this context problem required a genuine revolution, a breakthrough that changed everything, called the transformer architecture.
So, the transformer is a specific type of neural network. It was introduced in this now legendary 2017 paper called Attention is All You Need. And this new design was a game changer because it was built from the ground up for one specific job: processing sequential data like the flow of words in a sentence and understanding their context.
And its secret weapon? A mechanism called self-attention. Now, what this does is it allows the model to look at every single word in a sentence all at once and weigh their importance to each other. So if you have a sentence like, "The cat couldn't chase the mouse because it was too tired," self-attention is what helps the AI figure out that it refers to the cat, not the mouse. It's how it finally cracked the code of context. And this transformer architecture brought three huge, game-changing advantages to the table. First, parallel processing. It could process all the words in a sentence simultaneously, which made it way faster. Think of it like a multi-lane highway instead of a single-lane road. Second, scalability. You could just keep making these models bigger and bigger, and they just kept getting smarter. And third, transfer learning. This meant you could pre-train one gigantic model on like the entire internet, and then easily fine-tune it for very specific jobs.
All right, let's take a breath. We've covered a lot. We have the neural network, the artificial brain, we have tokens and embeddings, which turn language into numbers, and now we have the transformer architecture, which understands context. We have all the pieces. So let's put them all together and see how this creates the AI that so many of us are using every single day.
And it all comes together beautifully in that acronym you've definitely heard, GPT. The G stands for generative. Its purpose is to generate new original text. The P is for pre-trained. That goes back to what we said about transfer learning. It's pre-trained on a vast ocean of data first. And the T? That stands for transformer, the powerful attention-based architecture that allows it to understand context. The entire recipe is right there in the name.
So when you peel back all the layers, what is an LLM really doing? It's not thinking, it's not feeling. At its core, it is an incredibly sophisticated prediction machine. It's using all of that training, all of that math, to make a ridiculously good guess at the very next token that should come in a sequence. So no, it's not magic, but it is a magnificent, complex system of probability and pattern recognition. And that leaves us with a pretty deep question to chew on, doesn't it? If a machine can predict the next word so perfectly that its language is indistinguishable from ours, what does it even mean to truly understand?